Hello, hello, it's Mr. Pouts. Section 6.3 is about proving that a quadrilateral is a parallelogram. Sorry. Now, last time we talked about a bunch of different properties of parallelograms through a couple the definition and a few different theorems. We talked about how opposite sides have to be parallel, how opposite sides have to be congruent, opposite angles are congruent, consecutive angles are supplementary. We're going to put those to use today to prove the triangles are congruent. So there's your goal. I want you to write that down on your goal sheet to determine whether a quadrilateral is a parallelogram. So, what do you need to show? What do you need to show that a quadrilateral is a parallelogram? Well, we have 6 different ways. There's 6 different ways you can use to prove that a quadrilateral is a parallelogram. We're going to talk about those 6 right now. So, the first one, if both pairs of opposite sides are congruent. And that's going to be, it's not in your notes, but this is Theorem 6.8. The Theorem 6.8 says, if both pairs of opposite sides of a quadrilateral are congruent, then the quadrilateral is a parallelogram. Second one that we can use, this is going to be Theorem 6.9. Again, these are not in your notes as normal theorems. They're going to be in right here, these 6 things. So you have to write these down. Number 2 would be if an angle of a quadrilateral is supplementary to both its consecutive angles. I think I'm going to start writing typing these just because it's going to be harder for me to write on this screen. You can certainly write them in your own notes though. So if an angle is supplementary to both its consecutive angles. Now remember, consecutive angles, that's Theorem 6.9. Now remember, consecutive angles are angles that are next to each other. So angles that are next to each other, one angle has 2 angles on both sides that would be next to each other. Alright? Alright, now, next one. This would be Theorem 6.10. If both pairs of opposite angles of a are congruent, then it is a parallelogram. That's Theorem 6.10. Now again, these are kind of like you're saying the converse of the theorems we did last time, where we said if you have a quadrilateral, then we have both angles, opposite angles are congruent. This time we're saying if both pairs of opposite angles are congruent, then it is a parallelogram. So we're really doing the converse. All right. Next one. If the diagonals, now we're dealing with the diagonals. If the diagonals bisect each other, then we can prove that it's a parallelogram. That's Theorem 6.11. All right. And there's actually one more theorem. Now, this is a lot. But one more theorem. Theorem 6.12 says if one pair of opposite sides is both congruent and parallel, so if one pair of opposite sides is both congruent and parallel, then the quadrilateral is a parallelogram. We only have to do that for one side. Interesting. I probably should have put this in the beginning, but I was going to put this at the end. So that was Theorem 612. But the definition is another way to prove it. If you can just prove that um, both pairs of opposite sides are parallel to each other. That is from the definition. All right, that is the last way you can prove it. That was probably should have been the first way. But there are your six ways. Those are six different ways to prove that um, parallelogram is. I'm just trying to readjust here. This here, sorry. That a parallelogram or a quadrilateral is a parallelogram. We have one, two, three, four, five theorems and one definition. All right, and we're going to use those now. So, can you prove the quadrilateral is a parallelogram based on the given information and explain? Well, if we look at each one, we're going to try and use one of the theorems or definitions. This one, it looks like because of the way that we have these labeled, this is congruent to this is congruent to this, it looks like we have those two bisect each other. So in this case, we'll say yes. And my explanation would be one of those theorems if the diagonals bisect each other. So that would be number 4 here. The diagonals bisect each other, then it's a parallelogram. So theorem 611. All right, number 2, we have we're labeled one pair of opposite sides are congruent. Now, what does the theorem say about opposite sides, or angles, not sides? Both pairs of opposite angles are congruent. We don't know that both pairs are congruent yet, so not enough information here. Sorry, we need both pairs. All right, let's go to number 3. So we have that this is 136 and this is 136. We have that that's 44. If we can prove that this is congruent to its opposite angle, then we're good to go. So why don't we check to see what the measure of that last angle would be and see if it is indeed equal to 44. Um, so they'd have to add up to 360 total. So 136 plus 136 plus 44. And let's say it's 44. Let's see if they would add up to 360. So that would be 10, 12, 20. Carry the 2. 6, 10, 18. Oh, come on here. Or sorry, 16. Okay, the one. And that is 360. So yes, this would be 44 degrees. Which would mean that those angles are congruent. And by that theorem, then, we have two opposite pairs of angles are congruent. Theorem 610. All right, last one. This one we have that one side is congruent, and the other set of opposite sides are parallel. Now, if you look, I think we have to have one or the other. If we're dealing with sides of parallel or congruent. So number 1 here says both pairs of opposite sides are congruent. We don't quite have that. Number 2 says, no, no. And number 5 says one pair of opposite sides is congruent and parallel. We are dealing with two different sides, and then the definition is both sides are parallel. We don't have that. We don't have enough information here, so I think this is going to be not enough info. Now, there is a roundabout way to do that. We know these are congruent. Um, if these are parallel, then these two would be supplementary. Same thing with these two, because those are going to be same side interior angles. They'll be supplementary. These are going to be well, we don't know if those are going to be supplementary necessarily, but so we're going to leave it at that and say not enough information. All right. We're going to skip these four. If you want to do those on your own, we'll do number 11. Otherwise, those four we might do in class. Number 11, for what value of the variables must figure ABC, so parallelogram ABC, be a parallelogram? So, we are given a parallelogram with all the sides labeled, and they have different variables in them. So we want opposite sides to be congruent. This is dealing opposite sides. So this has to be congruent to this. This would have to be congruent to this. I'm going to do the top and bottom ones first because they have the same exact um, variable dealing there. So we can figure out what maybe the variable of x is. So 4x minus 9 would have to equal 3x plus 3. So you subtract 3x. You also add 9 to both sides. You end up with just 1x is equal to 12. Now we want to figure that out for y. So if x has to be equal to 12, we can plug that in here. And we can say that 2y minus 3 equals 2 times 12, which is 14, plus 1, which is 15. We add 3 to both sides here. We end up with 2y equals 18, and y would have to be equal to 9. Alright, so x would have to be 12, and y would have to be 9. I know I did that quick, but opposite sides have to be congruent for them to be parallel. I have two theorems here. For the sake of time, we'll just do the second one, or proofs. Um, developing a proof. This is in your notes, I believe. Given that triangle LPO is congruent to triangle NPN, so we know that LPO is congruent to MPN. So these two triangles here, the left and the right one, are congruent. We want to prove that this is a parallelogram. So let's start with the given that we have those triangles. Now there are some things that we can do here based off of NPM. Yep, based off of how that's written. By CP/CTC, we know that corresponding parts of congruent triangles are congruent. We could definitely say that this 1% of opposite sides are congruent, but we don't know anything about the other set right now. So I'm not going to necessarily say, like we can say that, we'll label that, but I'm not necessarily going to use that to prove it because we'd have to figure out if LM and ON are congruent as well. So let's look at the diagonals. Let's see if they can bisect each other. Based on the order of things, LP has to be congruent to NP. Also, then these would have to be congruent to OP, or PO, we'll say, just for the order of our triangles given there, would have to be congruent to PM by CP/CTC. Now, actually, with that, we already know that because they're congruent on each side, that LN bisects MO. And that, again, is just the definition of a bisector, a segment bisector. And with that, if we know that the diagonals bisect each other, we can then go ahead and say that LMNO is a parallelogram. Trust me, that says parallelogram. And let's go back to our handy dandy theorems and say if the diagonals are bisect each other, that would be theorem 611. Number 4 on our list there. 611. Alright, so there's the proof for you. What I'd like you to do on your own is to answer the closing questions. You're given two problems. It says in each problem below, can you prove the quadrilateral is a parallelogram based on the given information? And there's an answer given there for each one. Find the error. All right, we'll see you next time.